Good afternoon, everybody. I used to have the excuse that I'd be jet lagged, but I live back in the UK now, so I don't really have that excuse. So good morning, everybody. Good afternoon, everybody. This is like my first session of the day. I had a migraine last night, so I got up quite late this morning, so I'm a little bit groggy. And sort of, it's also that weird moment where you're quite sleepy walking over Westminster Bridge. And because there's so many tourists there, you know, you're hearing all these different languages. And I'm already a bit out of it, and I'm thinking, have I just got off a plane? Is there something weird going on? That doesn't look like Big Ben. And anyway, I got very confused this morning. My area of expertise is microservices stuff, so hopefully this will be a bit more on point. Thank you for coming along to a security talk. You are here to see a security talk from somebody who is really, I self-identify when it comes to security as being a conscious incompetent. That is somebody who knows he doesn't know much. And so I try and educate myself. And that's primarily that's the view place I come from. There are definitely absolutely experts out there, but I've learned this stuff, and so can you, right? That's my main driver here. And we're going to be talking about aspects related to microservice security, things that you might need to consider when starting or during your journey towards a microservice architecture. There are also going to be some things here that may well be of use to you inside your monolithic type systems as well, because, to an extent, all computer systems have some of the same characteristics. Many years ago, I wrote a book called Building Microservices. It was fortunate enough that it was just the first book of microservices. That was good. I've got another book on system decomposition, sort of monolith to microservice decomposition, coming out later this year. I now run my own company called Sam Newman and Associates. We do training, advisory, and consultancy work, really all across Europe, which is making Brexit an especially painful moment for me at the moment. So right now, we're not going to talk about that. We do live in a world, actually, especially those of us as technologists, where concerns around privacy and security are much more to the forefront. You see lots more news stories around data breaches and the like. You have things like the Equifax breach, where lots of personal information is getting stolen, and it seems like those reports are coming out on a near daily basis. I didn't realize these things were happening until I met Troy, and so I kind of feel that Troy is somehow correlated to data breaches in my head now. So I would just say don't put your data anywhere near him. But we'll talk a bit more about the Equifax breach later on. We've also, of course, got things now where our chipsets themselves have bugs and issues and security flaws in them that require us to have those patched as well, which is kind of a weird place. We're all much more aware of privacy in the post-Snowden era. And so security is being talked about a lot, and yet I still think when it comes to thinking about how we develop our software, security is still a bit of an afterthought. I think for many of us now, we think about the creation of software in terms of these sort of design, develop, test, deploy sort of loops, and we build in, quality, we build in usability, we get everyone really tightly involved in that process, we build it, we run it, we ship it, and then someone goes, security? Any security? No, that's okay. We'll sprinkle the security on later. Worry about that later. We'll sprinkle it on. We'll get some experts in. You can always tell they're experts because they use different language and they wear very different clothing and they use different acronyms you don't understand. And you'll bring them in and they'll just sprinkle that security in. And it's sort of where we were maybe 15 years ago when it came to things like testing. If you think about our approach to how we would think about testing in the past, as a developer, why would I need to write tests? I wrote it, therefore it must work. I wouldn't have written it not to work. Have somebody else check my work for me, please. And you had separate QAs and test teams. And we now recognize there's a good value in having people that really are specialists in their field, but the idea that they're separate from the delivery process, we understand to be really inefficient. We have the same approach really, again, sort of 15, 20 years ago, thinking about usability. You'd have a separate design ideation phase from the delivery phase. And again, many of you probably now work with experienced design people sort of inside your build and development cycles, which again is a much better way of shipping software. The reality is for some of that to work, as developers, you need a base level of understanding about some of those things to understand how to work with those sorts of people. And also to understand where is a kind of problem, something that I can do with myself versus getting somebody else in to do for me. Where is the limits between what is just enough security? For example, I think most of us know, I know how to write some functional automated tests. I'd love to have an expert with me as well. So some of the stuff I'm trying to share here is just enough security, little bits that you can fold into your daily work, which isn't going to take a huge amount of effort necessarily, but just baking that into your thinking in the same way many of you bake into your thinking around usability, around test, and all those sorts of things. We're doing this, of course, for microservice architectures, which give us some interesting challenges when it comes to security. On the one hand, they give us a better story around security. With a monolithic system, we tend to have all of our data stored in a single database, which makes us vulnerable to a particular breach. If one database gets hacked, all of our data is out there in the open, and that's obviously a bit of a concern. Likewise, an application, a single running stack with one critical defect, potentially makes all of our processing vulnerable. With a microservice architecture, because we've got these separate units, an exploit or an attack against one of those services may not necessarily affect those other parts of our system. And even if it does, because we are obviously isolating our data storage inside our microservice boundaries, gaining access to one service's data does not mean you're going to gain access to the data of any other services. So this microservice architecture gives you this possibility of defense in depth. You can isolate parts of your system, focusing your time, energy, and sort of also all that auditing you might have to do. Some of you might have to go through things like PCI compliance checking. If your system is all in one big giant box, effectively those sorts of compliance and auditing processes apply to everything you do. If you can break that apart, you can much better focus those parts of your organization that are focused on getting sign-off or storing health medical records or whatever else that is on those services that touch that data, and the rest can be excluded from that kind of work. And this can really help with things like GDPR as well. Better understanding where people's data lives, making it easier to retrieve that data when required or scrub that data as required. And this property of defense in depth is really, really powerful. Of course, on the other side, with a microservice architecture, we have lots of information that's flowing over networks that never flowed over networks before. With a monolithic system, that information used to flow within a single process. Now, it's flowing across networks between services. And all too often, I see with my clients that that information being sent between services is going over completely unprotected corporate networks. Networks where the crispy outer shell pattern is adopted. The crispy outer shell pattern is where you have a big wall, and the big wall around your network says no one will ever get in, without ever asking yourself the question, what happens if someone does? It doesn't matter if you've got a massive, great big front gate on your building. If you've left the back door open and someone gets inside, what happens then? And when you only have that one perimeter, you sort of have issues around this. So people get inside, and they can maybe start looking at the data that's flowing between services, potentially manipulating that data, or directly accessing those endpoints themselves. And for some things, having a larger attack surface area might be more of a problem. You've got more systems that need to be looked at, monitored, patched, and protected. What we're going to do is we're going to rattle through a few basic things very quickly first off, though. So who here thinks they're very good at assessing risk? Now, of course, you're not going to put your hands up, are you? Because I've obviously made one person, brave person here. Because I've asked you a leading question, and you know the device here. I'm going to ask you the leading question, and I'm going to come in and show you that you don't know what you're talking about. Turns out you're actually quite smart about this sort of stuff. That's fine. A lot of security, when it comes to sort of delivery, is actually about assessing your risk and assessing where you're vulnerable. As technologists, I think we're all too often drawn towards the big, shiny stuff. So when people want to talk to me about microservice security, they want to talk to me about transport security and authentication authorization protocols and confused deputies, and we'll get to that. But they've skipped over a lot of the low-hanging fruit, the things that you can do that actually are where your systems are most vulnerable. I do urge all of you, actually, if you haven't done so, to make sure you've had some kind of good threat modeling exercise where sometimes external people, but you can often do it yourself, will look rationally at your system and tell you, yes, it's very good you're focusing on that lovely portcullis and moat and giant wall, and these are towers to defend your building, but maybe you've got putting a small fence up around the back would be a good idea as well. So there's a really useful report that comes out once a year called the Verizon Data Breach Report. The 2018 version only came out, I think, towards the end of last year, so I haven't updated this slide yet. This looks at data breaches for all of Verizon's customers, which is mostly a North American business, so there may be some geographical skew. And they looked at all the data breaches, and they were looking at the mechanisms used by attackers in those data breaches. And they found that in over 80% of all the data breaches they saw, that weak or stolen credentials were part of the problem. So more than 80% of those things. Now, this is probably not news to many of you, but the use and management and storage of passwords remains a big issue, and credentials as a whole. There is now better and good advice out there about how to deal with passwords, which is still not often being taken up by companies. Troy has an excellent write-up all about this. I do urge you to go and read his blog post on this subject. Troy's actually just summarizing information here from NIST in the US and the UK Cyber Security Centre. So this is actually from government agencies, and it's good advice from a government agency, which is not something you normally hear at a technology conference. There's loads of basic, good, useful stuff in here. Things like longer passwords are a good idea. I'm looking at you, Microsoft. I had to sign up. I bought a house. To buy a house, you have to get a mortgage. To get a mortgage, at least with my bank, I needed to sign up for an Office 365 license so I could open a Word document. I thought buying a house was stressful enough as it was. No, taking out an Office 365 membership seems to be on par. And then I have to create a password for my account, and I'm limited to 12 characters, which is weird when you think about what they do with passwords, because passwords are hashed normally into quite a long string and then stored. And so by limiting me to only having 12 characters, you're actually limiting the amount of entropy I can give you in order to create a password that's hard to hack. Bits are not expensive. 12 characters is insane. Long passwords are better. Actually, if you make things longer, you can often relax on some of those stupid complexity rules. Oh, you have to pick an exclamation mark and some sort of weird hieroglyphic character. And often this happens because people say you can only have a short password, and therefore they need to add more complexity into that short password to get the entropy needed to make them hard to crack. What do people do? Capital P, @ 55, W, 0, ORD, exclamation mark, which is in every dictionary hack crack system out there, right? So people end up with easily guessable passwords using these rules. So don't do that. Password managers. Who here uses a password manager for your personal passwords? OK, fantastic. That's, I'd say, about 85% of you. Now, how many of you use a password manager for the passwords you use at work? Less people, which is really disturbing. Actually, that's kind of odd to me. So you take more care and attention over your own personal passwords than you do the credentials you use at work. You might want to ask your bosses about that, but you should have a password manager at work as well. Don't mandate password changes. This is weird. People get surprised by this. Do not mandate password changes. Because what happens is when you're prompted to always keep changing your password, you're tuning people or training people to expect a pop-up once every 3 months saying, please enter your old password. Please enter your new password. Thank you. And then what happens is, over time, you end up getting phishing attacks, and you're just used to, oh, for God's sake, I want to get on with my job. I'm just going to type my old password in and hit OK, and I'm sure nothing will possibly go wrong. So do not mandate password changes. Only require that to happen when you think those passwords may have been hacked. And of course, there are loads of systems out there now to help you track down when those passwords have potentially been breached. Have I been prone to being chief among them? There are other types of credentials you might need. There are some areas where you do sometimes want to limit not only the duration of credentials, but also the scope of credentials. Has anyone here heard of a company called Codespaces? I mean, you can probably guess why you haven't heard of them before, because of the big explosion saying they no longer exist. So Codespaces was a company that provided, and this is a slightly ironic statement, secure source code hosting. And they ran their whole system on Amazon, and somebody got hold of effectively the root administration credentials for their AWS account and deleted the entire running production system. And no one was out. I don't think they ever found out if it was an disgruntled ex-employee or they just left these credentials lying around. It was some sort of script kiddie. But they wiped out the whole production system, so the whole system went down. And then you're thinking, well, Sam, obviously that wouldn't have been a problem if they had backups. Oh, yes. Of course, they did have backups. Anyone want to guess where they had the backups? They had backups in the same Amazon account. So when you talk about off-site backups, it doesn't mean they're physically not in your, it means they're off-site from the production system you're backing up, not that they're not at your house. So they had the backups in the production environment, so that had all gone. But that's okay, they had the source code, right? Yes, they had the source code. Anyone want to guess where the source code was? Yes. So a couple of problems there. You know, when it comes to cloud-based accounts, having a separation of concerns can make sense. I think it's always a good idea to have strong separate production, dev, and test accounts. If I have multiple teams all deploying services as part of an overall system, I may even have separate production accounts for each of those teams. That way, if one of those accounts is compromised, you limit the impact of that compromise. Also, limiting how long these passwords are valid for with things like AWS API keys is actually very, very easy to do. There are tools out there that will also help pick up API keys that may have accidentally been checked in. I've used GitRob in the past for combing corporate Git repositories. It will look for strings that look like they may be private or public API keys. Amazon themselves also do on occasion scan public repos looking for those sorts of things. I know of at least one of my old clients that was taken for about $15,000 in AWS spend overnight through Bitcoin mining because of this sort of stuff. What tends to happen with leaked cloud credentials is not that people shut your stuff down, because then you tend to notice. It's much more likely that they can start cranking up computing resources and doing some Bitcoin mining. And there are some very, very expensive per hour GPU-based computers out there that they will buy with your credit card. Now, the problem with one of the ways we limit this sort of stuff is we limit the scope of credentials, which is one part of it. But what you can also do for things like API keys and those sorts of things is rotate those credentials. If you think about computer-to-computer credentials, things like database, username, and passwords, it's often a good thing for those things to be tumbled periodically. But that gets quite complicated in a microservice environment. With a monolithic system, you probably have one configuration file, one set of credentials you need to change. In a microservice environment, of course, there are loads of different machines running all over the place. Well, you've got lots of different logical services. Those logical services may themselves be scaled out into different physical instances. There are configuration files maybe sitting there with these credentials out there. When you need to change them, how do you do that? It's a bit of a daunting prospect. So we've got things like shared secrets that you might be using, which could be things like TLS certificates. They could be things like public-private key pairs, API key pairs, all of those sorts of things. Just something as simple as, how do I talk to my database? I've got a text file. Here is my credentials for talking to that database. If someone gets hold of that text file, they can directly accessing my database itself. For some of the cloud platforms, some of the container platforms I've worked with, you will actually pass passwords into the running process via environment variables. And there are some attacks where you can actually view environment variables being passed into a process, thereby getting runtime injected passwords out of them. And so that's not good. So one of the things you want to do here is if you can keep rotating these very, very rapidly, then you create a situation where even if someone gets hold of them, they're not useful for very long. And this is where things like secret stores can be really useful. Now, some of the cloud platform providers do provide good secret stores. I haven't used those on Azure, but you've got things like AWS Key Management Service and Parameter Store on Amazon, which many people really like. But I think the gold standard for secret stores out there is Vault. Vault is an open source tool from HashiCorp. They do some commercial add-ons to it as well. And it's a very, very powerful mechanism for issuing and rotating credentials. You can also do things like encrypting fields for you as well. And so you could use these sorts of systems for doing things like encrypting potentially passwords, credit card numbers, and details as well with these sorts of systems. So the Vault instance itself works in kind of an interesting way. One of the nice things it does is it can talk to databases on your behalf. So your application could come along and say, what is the username and password to talk to my database? Vault itself will then go and talk to that database and will create your own username and password pair. This is just like having your own a different password and email address combination for all of your public accounts. It can do this for every one of your services. It can create a time-limited username and password for things like Postgres, MySQL, Oracle, give you those credentials in your application. There's a whole workflow behind how you just reissue those credentials. And that's really powerful because then that's a centralized system that's managing these things on your behalf. You can also do the same things in terms of automatically issuing API keys from the cloud platform providers. And a lot of organizations I work with actually use these systems for humans to get time-limited API keys for things like launching Amazon resources or Azure resources and things. Vault also has this API you work with, and your program can use that API to get the secrets it needs. Of course, that's a bit of a pain. Most people's applications tend to be configured via text file, which is nice, right? We like putting things in text file, and Vault can solve a problem for you there as well, because it works with a sister tool called Console Template. And Console Template basically dynamically updates text files based on information stored centrally in either Console or Vault. So you can have a template that looks like this. This is saying, this is my Postgres connection here. I need a username and a password. And Vault, when those values change, Console Template will update them for you dynamically. So if you suddenly want to revoke that, you want to change it every half an hour, you can, and it will roll those changes out on your behalf. So certainly if you want secret stores, you look worried about secrets being stored across multiple services. You could use this for certificates as well. It's well worth a look. And if you're running on, say, something like Kubernetes, Vault itself is effectively stateless. It stores its data onto something else underneath it. So it encrypts and stores data on things like Console or etcd. So this is a good drop-in replacement for the Kubernetes secret storage solution, which is pretty poor in the grand scheme of things, if you're in that world. Let's look at some of the other risks out here. This is a bit of an earlier report here. This is from Forbes BMC back in 2016, which says that 44% of security breaches occur after vulnerabilities and solutions have been identified. And they could have been avoided if those vulnerabilities had been fixed. So a large proportion of breaches are occurring for known vulnerabilities. These aren't zero-day exploits. These are things where there was a bug, they issued a patch, 6 months later, you still haven't installed a patch. Guess what? Someone's worked out how to create an exploit in NIST, and now your system is cracked. A great example of this problem occurring very recently was Equifax. So Equifax still is, a sort of a credit checking agency in the US. It's also used by some UK companies. They were hacked, and 143 million records were stolen. Now, when you say records, these are all sorts of information these organizations gather on you to give you a credit score. So this is quite detailed information. This is a lot of information. Now, the defect that actually affected Equifax was a defect in the Struts web application framework, which is, in the grand scheme of things, quite an old framework, but it's still actively maintained in the Java ecosystem. So here you can actually dive into the bug. So this is the CVE database telling us about this defect. And the CVE database gives us a score for how bad this defect is. And you can see that score there is 10. So that's 10. Now, 10, it's not out of 100. It's out of 10. And this isn't at the good end of the spectrum, right? So this is about as bad as these defects can possibly get. Now, actually, the people that found this did the right thing. They spoke to the maintainers of Strut, said that it's got this problem that's coming out. We need to fix it. The problem, the vulnerability was so critical that they wanted to get the announcement of the patch out, the announcement of the vulnerability out, and the patches available on the same day, and encourage everybody to update. So it was reported publicly in 2017, and on the 7th of March of that, basically the same day, you had patches on both the major branches of Struts available. So very, very quickly, they got those things out to avoid any nasty 0 days. So they did exactly the right thing. There's nothing else they could really have done at this point. So what happened at Equifax is that they know that between mid-May and July of that year that this data was stolen. Not quite sure when. It's always fun. We lost your data. Not kind of sure when. So they noticed in July, but anywhere between then and mid-May, this data could have gone. So Equifax themselves saw it on July the 29th, and they did a really nice thing. They waited a long, long, long time before telling anybody about it. So they reported this on September the 7th. So there is no mandatory data reporting requirements in the US. It's another example of what GDPR has done well. So a big gap, right? So by the time they found this defect, anywhere this data had been, between the patch being issued and the data being stolen, it was anywhere from a 2 to a 4-month window. So if they'd applied that patch anywhere in that 2-month window, they definitely would have avoided this problem altogether. They didn't, and so they ended up testifying before Congress. Then there's a nice little tidbit of information here. Between them finding the problem on July the 29th and reporting the problem publicly on September the 7th, purely by coincidence, a bunch of Equifax executives sold a bunch of their stock. It was, there's nothing untoward about that whatsoever. It's definitely not insider trading, is it? They could probably sue me if I'm wrong. Anyway, they did do it, so, it's on them. So 2 to 4 months, that's how long a window they had. 2 to 4 months, quite a big window in the grand scheme of things. And so some people were quite smug about this. Oh, it wouldn't happen to me. We wouldn't use struts. That's not really the point. It's not struts that's the problem. How many of you here know you patch all of the systems you use every 2 to 4 months? Put your hands up if you know that you do this, if you're sure. OK, we've got a few brave souls. Let's test this. The problem is, especially with microservice architectures, the way we deploy our software is a little bit more opaque. We are now deploying onto abstraction layers that themselves are deployed onto abstraction layers, right? It's becoming like a Russian doll situation, only inside each of the Russian dolls are more Russian dolls in parallel, and it gets very confusing. And then there's Kubernetes in there somewhere, right? So if you think about, say, a modern deployment stack for, say, a container-based microservice architecture, we'll start with our underlying hardware. Running on top of our underlying hardware, we have the operating system. Running on top of the operating system, we have the hypervisor. This is what's called Type 2 virtualization. And this is a typical type of virtualization found if you're using, say, Azure or AWS's managed virtual machines. This is also what vSphere does, VMware. It's a very, very common style of virtualization. The hypervisor maintains isolation between virtual machines and maps physical to virtual resources. On top of that, you'll have a virtual machine operating system. This will be where you'll be running your full-fat Windows operating system or the like. On top of that, you may then run a container engine. Maybe you're running a Docker or Rocket or one of the other container engines that might be part of a larger container-based cluster. On top of your Docker operating system, you then have your container operating system. People forget you do run full operating systems inside your container. And on top of your container, you have your application with its third-party dependencies. Now, in Equifax's case, it was a little defect just up here that caused that data breach. So this is a not unfamiliar stack diagram. Now, as developers, we often only see a small part of this, but that's what's happening under the hood. And guess what? Every single layer here needs patching. Every single one. So how many of you are still really confident that all of the things on the systems you rely on are patched every 2 to 4 months? 3 people. It's all right. That's pretty good. It's depressing, but it's good, right? It's right. And often the thing is, and some of you think you might, but you're not sure. That's the other thing. Visibility, we don't know. Right? So that's not great. There are things we can do about this. I mean, one of the first things, obviously, you can do is offload work. Right? If you're going to a cloud provider and you're using managed virtual machines, so EC2 on AWS, the underlying cloud provider is looking after the physical hardware, the operating system, the hypervisor, and they're looking after that part of it for you. And we see this in practice when Spectre and Meltdown's patches were released. All the cloud providers applied those patches well within 7 days of them coming out. And you can see that happening because everyone's machines got 30% slower within 7 days. I mean, the fact that by applying the patches, they effectively increased their profit margins has almost got nothing to do with it. Anyway, but we offload it. We can pass this off to a trusted party that we assume will handle it for us. If we're using a container-based platform that's given to us by a public cloud vendor, again, we've got even more of it being handled by someone else. We've got they're running the Kubernetes system. You're using Fargate or ECS or one of those types of systems. Even more of this is being handled for you by the underlying vendor. But even in this situation, you've still got your application and your container operating system that you have to deal with yourself. Function as a service takes it that little bit further, where they're even maybe handling effectively the containerization layer is being handled for you. Because we know the containers are under the hood for these function as a service frameworks. but you still have your function and its code. Now, when it comes to looking for vulnerabilities in containers, there's been some options out there for a while. So even if you're deploying containers onto systems, you've got open source tools like Claire, but Claire's sort of, it's all right to a point, but it does suffer certainly over time in terms of longer run times and doesn't really, out of the box, have an answer for the runtime problem. But you've got commercial tools like Aqua, which is really good at looking at vulnerabilities in containers. It's well worth a look if you're concerned. One of the problems with microservice architecture is often you create a service, it's quite small scoped in what it does, it doesn't need to change, and so it's out there running for 6 months. That's basically an operating system that hasn't been patched in 6 months. Would you know if in that 6-month running process you had a vulnerability that hadn't been patched? And it's like, oh, okay, I'm not sure. Things like Aqua can really help you. That's great on the container-based front, but that wouldn't have helped Equifax pick up their problem. And here you've got tools like Snick that can really help. Actually, out of interest, if everyone here used Snick? A few people, a very small number of people. You really should. It's a really nice tool. It works. Somebody's talking to me over here. So Snick works in a really simple way. It scans your source code repositories, and it looks for your dependency files. It understands different technology stacks. So it will look at the dependencies you have. The Snick team curate this big CVE database on the back end for these different technology stacks. And they'll say things like, hang on, you're using version 1.1 of this YAML parser library. That's got a critical vulnerability. Here's the critical vulnerability. There's a new version available which fixes this problem, so you should upgrade to 1.2. And they can do that as part of a build process or in a background thread. So you can actually use it to fail builds. You can also have that done on running systems. It goes further than that. It will even send you a pull request saying, oh, and by the way, I've taken the liberty of auto-generating an update to your dependency file so you can get the latest version of this NuGet package. Click OK. This stuff costs you like a few $100, a few £100. Well, actually, with the current exchange rate, that could be close to our GDP, I don't know. But it's quite cheap in the grand scheme of things. And certainly for Equifax, you think for the cost of $1,000 a year, it probably would have paid for itself several times over. So it's well worth a look. And they've even now got support for doing that live on running functions, running on the fast platforms, which is kind of cool. So this is, again, it's just easy stuff. And it's not too hard to keep an eye on this when you've got a single monolithic application even, because you're building and rebuilding and redeploying that monolith so quickly, you're much more likely to update those versions and those dependencies. But when you've got microservices that are sitting out there running dormant, well, not dormant, they're running, they're doing a job, but haven't been touched by anyone for a few months or maybe even a couple of years, this stuff is much more problematic. There's other good stuff out there, of course, you can look at. Doing threat modeling, I mentioned earlier, Microsoft have got some great write-ups of how to do threat modeling over at the Secure Development Lifecycle website. I will say it's a bit waterfally in places, but there is some good advice there. And if you want really nice overviews of things like Stride and Dread, do take a look. But let's take a look at some of the more complicated issues that occur in microservice architectures, and we'll take a look at two last topics really, which is around transport security and around authorization and authentication challenges. So taking a look at a very simple version of a microservice architecture, this is my common music shop. I'm still selling CDs against the tide of everyone else now buying LPs again. So this is our little microservice architecture. We've got a few upstream clients using mobile devices and web devices, and we've got some sort of trusted third party we talk to on the back end. But this is our sort of perimeter. And so the next level of concerns we start thinking about is, well, how do we protect all this information that's flowing across our systems? So how do we protect those lines? What do we need to do about those lines to make sure that they can't be intercepted or manipulated by external parties? There's kind of like 4 key concerns when we start thinking about transport security. The first is thinking about observation of data. Can people we don't trust view what's going between two services? The second is, can they manipulate that data? So are we vulnerable to, say, a classic man-in-the-middle attack where somebody says, rather than paying Sam £100, I'm now going to pay Sam £200, which would be great for me, maybe not you if your goal was not to spend me £200. We also want to make it difficult for people to access endpoints that they shouldn't otherwise access. A lot of people I work with, they say, it's OK, we've got HTTPS, but it does nothing about restricting access to a server. It doesn't do that. It's not what it's for. or by itself anyway. And you also want to stop impersonation of endpoints. This is a bit more of a theoretical attack. Well, not theoretical, but it's not something that's likely to happen. But there have been some sort of proven, albeit not seen in public attacks, where people can do things like create a fake Kubernetes node on your corporate network, pretend to be part of your cluster, and then someone starts sending you work, which you then have full access of. It's kind of it's a niche type of problem, but it does occur. So if we start with something like HTTPS everywhere, which is now very easy to do, and obviously we talk about it a lot on the public internet, it does have some value, though, within your perimeter. It gives you server guarantees, so that stops that impersonation of endpoints. You get some guarantees that your payloads have not been manipulated, which is good. By itself, if we're just talking about server-side certificates, you're not going to get client guarantees. And historically, people complain to me that certificate management can be painful. I would say in this day and age, if you find server-side certificate management for HTTPS too painful for you, then you shouldn't be doing a microservice architecture, because there are way harder things to deal with out there than this. Especially when you've got everything out there from, Let's Encrypt, which is now free, and more importantly, automated. All of the cloud platforms out there now support this stuff really well, and often for free, as in $0, for managing these server-side certificates. And with things like the API gateways on both Azure and AWS, you can even set up termination of those things as well. This is not hard. If you can't do it, in all seriousness, you probably should rethink whether or not you want to embark on building a microservice architecture. So this stacks up fairly well, even at the simple level, right? It stops data being manipulated. It stops data being observed. It doesn't by itself do anything about restricting access to endpoints, which you've got to sort. And it does stop impersonation of endpoints, assuming you validate your certificates. I shouldn't have to say it, but it's still amazing to me how many of my corporate clients just turn that off because it's faster. It's definitely not safer, is it? It's even worse because you think you're protected and you're not. So obviously, this becomes just a sensible default choice maybe for inside your network perimeter, and obviously publicly. With public use of HTTPS, with server-side certificates, we don't worry as much about client identity, because client identity is provided by the human being authorizing themselves with us, authenticating themselves with us. MutualTLS takes this to the next level, where we actually also have the clients themselves having certificates too. And so we basically get that two-way trust. Now we can verify not only is the server who I think the server is, but the server can say, yes, that is a client who is allowed to talk to me. And this is sort of fixing that last part of the problem for us. So we get client and server guarantees. Again, certificate management here can be more painful. And I think, again, more for people that aren't on the cloud providers. Service meshes can make this a bit easier. If you're using things like Istio, Istio can help roll out MutualTLS. If you're not and you're running on-premise, I do have some sympathy for you that making this stuff work can be difficult. I've done this before with things like using Puppet and Chef to roll out certificates. It's fiddly. Again, public cloud platforms, though, really do have this wrapped up. It took me all of about 30 seconds to find this great, really detailed, very thorough write-up on how you do MutualTLS using Azure's API gateway, right? So it's not actually on the cloud platforms. Again, there's not really a good excuse for that stuff anymore. So this is great. MutualTLS is excellent. Observation of data, tick. Manipulation of data is stopped, tick. We restrict access to endpoints, tick. We stop our endpoints being impersonated, tick. This is good stuff. Now, of course, many of you will communicate using protocols that aren't based on HTTP, but many other protocols can still make use of these same protections using TLS over other types of protocols. I'll skip over that. So you might be using, say, some sort of message broker technology. You might be using something like gRPC, which is a really good RPC protocol. gRPC sits on top of HTTP2, and so obviously can take advantage of MutualTLS. If you're using things like Rabbit or Kafka, you'll have to look at, they actually both support their own kind of protection mechanisms for data in flight. So you will need to look into that documentation yourselves, but you can certainly get TLS support on Kafka. So we've solved sort of the problem about how do we protect access to our endpoints from other computers. And how do we make sure the communication between two computers is protected? The problem, of course, is that, as always, it's not really computers that we're worried about. It's human beings, because it's what the humans do in this mix that causes us the other headache. In this situation here, what we'll normally do is, when human beings want to come and access our system, we will ask them to authenticate themselves. We'll say, Bob will say, I want to log in, and you'll say, are you really Bob? Can you prove that you are Bob? And Bob will say, yes, and I'm going to prove I'm Bob by giving you my username and password. That's great. Maybe there's different schemes out there, most likely using some form of OAuth protocol for mobile. So I log in, and it's typical to have like an authentication gateway that sits on your perimeter that effectively handles that handshaking. And so it will look for the presence of a logged in sessions token. If you don't have one, it will redirect you. You'll get logged in, you get the token, and once you've got that token, the auth gateway will allow requests into your perimeter. So effectively, you can adopt the mindset that once they've got past that gateway, they have been authenticated for those paths. This is typically a separate appliance. You might take an existing proxy or perimeter device you've got setting up and configure that in there. It could be Nginx. You might use an API gateway for this. Some organizations I've worked with actually do this work inside the services themselves. So any service that sits directly on the perimeter will have a library for handling this redirection flow. And that is primarily to reduce adding additional network hops. For the vast majority of the people I meet, adding a few milliseconds latency to these operations is not a concern. So in general, just stick it in an upstream proxy. So this is fine. So now only if you're logged in can you access the protected servers. But the bigger question here is, how do we handle something like authorization in this type of environment? So, because we've got the authentication flow, which is Bob comes along and says, I'm Bob. And the gateway goes, yeah, I'm sure. Can you just for me, can you show me that you're Bob? OK, yes, I'll log in. And then you're logged in. Great. And now I go to the music shop and say, I want to see my account, that sort of thing. So in this situation here, Bob actually wants to access his profile. He's going to click the profile button on the web page. But the profile button contains information that the music web shop in this situation doesn't have. So the music web shop serves up our good old-fashioned HTML pages. But some of the information comes from downstream sources. So let's take a look at that. So I'm logged in as Bob, and I maybe end up going to a URL like this. So I say, can I have access to my data? I've been logged in, so I'm authenticated. So the request comes through. The music web shop says, oh, you want to see your page? I'll start rendering it. Oh, to render this bit, I'm going to have to make a downstream call now. So I'm going to go to that downstream service, fetch the information I need to render it. So I'm going to go to the user service to get your data. So off you go. You go down to the user service and say, can I have Bob's details? And the user service at this point says, well, you're the music shop. I trust you. I've seen you around this place before. You've got the right certificate. You wouldn't ask me to do something I shouldn't do, would you? You're my friend. So the data comes back. Bob's data comes back. And the music web shop uses that to construct a nice profile page. And voila, at this stage, nothing's actually gone wrong. Bob has access to Bob's data. That's nice. Bob, of course, as we know from looking at any paper on security, is always up to no good. And so Bob starts looking at that URL and goes, oh, I wonder what happens if I change the word Bob for the word Alice. Let's see, can I see Alice's data? So the request comes in. The auth gateway says, are you logged in? And there's a token. Oh, you're logged in. Great. I'll send the request downstream to the web shop. The web shop says, well, I don't actually restore that information, so I'm going to go and ask. And you go to the user service and says, can I have Alice's details? And the user service says, you're the web shop. You wouldn't do anything that you shouldn't be able to do, would you? I trust you. This is effectively implicit trust at this point, right? And so back comes Alice's data. And Alice's data gets put into a nice page. And then what we've seen here is Bob accessing Alice's data. So this problem actually happens more than you think. It's not something we would like to happen. This is actually an example of what's called the confused deputy problem. And a confused deputy problem is something that occurs when you trick an intermediary party into doing something they shouldn't be able to do. In this situation, effectively, we've done that, right? What we'd like to do is actually authorize the request and say, what is Bob actually allowed to do? Because we've authenticated Bob, but we haven't authorized what Bob is allowed to do. So clearly there's an authorization problem here. Somebody should have said, no, hang on, if you're Bob, you can only access Bob's data. The question is, who makes that judgment? Who decides what Bob can do? And more to the point, what information do they need to make that judgment call? We could, for example, authorize Bob upstream. So at this point, we know that this person is Bob because we know they have authenticated as Bob. So we could say, the thing you're trying to do, you're not allowed to do. But for that to happen, I would need to be able to know that the request coming in is going to result later on a downstream call to a service to access some functionality that we are going to restrict. And so that basically means is that some service downstream is a capability I'm trying to access here, and something upstream needs to magically know that that capability exists and stop you from accessing it. And that just breaks my brain a bit. I'm not sure how that's going to work. In an environment with microservices where we're trying to create fast, autonomous teams where you get things done, every single time I roll out a new feature, do I now have to go and configure something in some upstream centralized service? The other thing that can sometimes happen is you let the request come down here, and the user says, oh, I'm going to go and check what you can do, and goes to some central service, thereby adding additional network hops to our flows. And that's not great either. The model that always made more sense for me is for downstream services where this functionality lives, that they should be able to make the choices here. Right? So the feature, the functionality we're accessing is downstream. The downstream service should be able to say, yes, you can do this, or no, you can't. But for that to work, they need to know who the user is. And often at that point, they've got no idea who the user is, because that information was lost a long time ago. So that's what we're going to try and fix. What we want to do is the user service to say, hang on, you want to access Alice's data, but you are Bob. And based on how our system is configured, that is not something you're allowed to do. So then the question becomes, how do you get information about who the originating request is down to a downstream service? Now, this is technically possible with nested SAML assertions. Do not do that. Do that. Tried it for a bit. Went a bit crazy. Met a team in Norway that did it for 6 months, and it looked like they'd been through hell and back. So don't do it with nested SAML assertions. There are much simpler techniques out there nowadays. One of the easiest mechanisms here is something called JWT Tokens. So JWT Tokens is a mechanism by which you take a JSON payload, and you basically encrypt and hash it into a token, and that token can be sent downstream. That can contain information about a person, what they're allowed to do, maybe the groups they're in, the roles that they have. That token can be validated without additional round trips. So servers that receive that token can, just by using a public key, for example, there are different signing mechanisms available, validate whether or not that is a real token. So this is a very simple example payload. So I might have an ID of this user and their name. And you'd end up with looking something like this. This is actually straight from the JWT webpage. This is actually what a JWT fully signed token looks like. You've got the header, the payload, and the signature. And so there's loads of libraries out there now that will parse these things from you, and then you just need a key or something similar to actually verify the signature. So in this situation, the way that would work is Bob is logged in. Now, when Bob is logged in, he's got some kind of token to represent his logged in state that he was given to him when he did that original authentication. That could be an OAuth token, could be a cookie saying, yes, I'm logged in, here's who I am. Normally, what you would do with JWT tokens is you generate the JWT token inside the perimeter. So at that point, I would effectively exchange that token for a JWT token about Bob that could contain information about them. That token, which might be as simple as that, would be sent downstream. The user service would get it, and it'd say, you want Alice's details? Well, the first thing we'll do is make sure you are the web shop. Great, you are. Next thing is, let's look at this token, validate the token. It's a valid token, but this token says you are Bob, and unfortunately, you've asked for Alice's information, and therefore, that is not something that you are allowed to do. And so we would say no and pass that information back. You can generate these tokens and store them actually on the client device. The one issue there is that some people are a bit more concerned about what data they're storing in those tokens. There's also more of a concern then about expiry of these tokens. If you're only generating those tokens inside your perimeter, you can keep much tighter expiry on them because they only need to exist for the duration of one set of requests. You can, of course, put lots more data inside these things if you want to. You could put the groups Bob is in. You might have more complex rules. Maybe the rules are users can only see their own information unless they're also in the admin group or the customer support group. Now, this isn't a universal solution for all problems. One of the clients I was chatting to did music rights management. And in some parts of their system, the authorization rules were incredibly complicated. And my client had done some work and reckoned that to put all the information needed in the JWT tokens to do that authorization, the JWT tokens would have about 20,000 fields in them on average. The approach we ended up there with was saying, well, for most of your authorization needs, you actually need about 5 fields, so let's keep it for that. And in those rare situations where you need the much more detailed information, you accept you might need an additional round trip to check in with some central authority. So you can balance those forces a bit. Last note I'm going to leave you with is there are these things coming called service meshes, and these may be of a special interest to you if you're working on a containerized platform. Service meshes are effectively middleware for synchronous communication, and they give you the ability to solve, or at least implement some of these technologies I've been talking about in a more centralized manner without you having to worry about it inside your service. So probably a couple of the most popular out there are Linkerd or Istio. Linkerd version 1 it's been around for the longest, actually. It's very widely used. Monzo used this very heavily and are big fans of it. Istio has obviously been pushed very heavily via Google and sort of goes very well with Kubernetes. Service meshes exist and they solve quite a cool problem in a whole multitude of problems in a fairly cool way. And my concern around them primarily is sort of the maturity of the implementation rather than the idea itself. But let's take a look at the average type of concerns that two services might have. We've got a service calling another service, and there are a bunch of common concerns we have with service-to-service communication. And it might be something like tracing. So how do I know how long these calls took? So I've got to put some code in both services to make sure that the tracing is being tracked accordingly. When it comes to, I might be doing some load balancing and service discovery logic in those services. That's a bit more common code I've got inside them. When it comes to security, I've now got authentication mechanisms in here. I might be doing things like my JWT tokens, signing and checking. Maybe I've got API keys to worry about in terms of how I'm authenticating a transport. I'm using something like HMAC. I've got those certificates that need to be shifted around and things. I've also got all this other stuff around connection resiliency and retries, like circuit breakers and all those sorts of things. And we end up with this whole stack of common stuff that we want all our services to be able to do to give us that base level of can A talk to B the way we want A to talk to B. And one of the ways you solve this is by creating common libraries and common frameworks. In the Java ecosystem, for example, you pick up Spring Boot, and you can get a lot of these things out of the box. And lots of different technology stacks have their own common flavor of this. Microsoft, of course, you've got Service Fabric, which arguably is a much bigger beast, but covers off some of these concerns as well. And that's fine if you're adopting the same technology everywhere. So if all of your ecosystem is, for example, running Spring Boot, well, then a common set of libraries and frameworks might be a good idea. But of course, one of the powers of microservice architectures is that we want to keep ourselves open to using different technology stacks and using different runtimes. But if we're relying on shared common code to do that, how's that going to work? So I might have my shared code or my reusable code for my authorization and authentication stuff for my Java services, but do I have to re-implement those for a different technology stack? Or do I get a different framework for my .NET service here, but that .NET service might have a different set of conventions for how it handles those things? So is it going to be able to handle this in a consistent manner? And that becomes an ongoing piece of work. A lot of organizations, actually, because of this, will actually limit the amount of technologies you're allowed to use in your microservice environment. They'll say you have to use, for example, the JVM for deployment because we've invested time and energy in getting these libraries right for the JVM. And so we know if you use the JVM, you can use this code, and that code works properly. Another issue that occurs with these things, if you're relying on common code to handle things like authorization, authentication across service boundaries, is that over time, versions can drift, right? A newer service comes out that I'm talking to, they've got a newer version of that library, the behavior is slightly different, that can be a bit of an issue. And Netflix is one of these organizations that said, when you talk across a network, you will talk on the JVM to the JVM, because we've invested thousands and thousands of developer hours into creating libraries like Eureka and Historics for handling service-to-service communication, and we know they work. And we know they have predictable behavior under load. We've worked out how to make Netflix successful with this sort of technology ecosystem. If you bring some new technology stack in, we're going to effectively expect you to re-implement all of this stuff again, and is that going to work? You can do a good job of that? But of course, they also wanted to be able to give people the opportunity to try a different technology stack. So what they said was, when you talk across a machine, you have to talk over a network. When you have to talk over a network, the JVM has to sit at both ends because it can run that common code. So for non-JVM languages, they adopted what they originally called the Sidecar model. With the Sidecar model, you basically wrote the service in whatever language you want to write it in. Could be Node, could be Python, could be .NET Core, whatever. It would then talk locally to the JVM, which is effectively at this stage running like a proxy. That JVM is now kind of a generic piece of, a generic proxy. It doesn't know anything about your actual service, but it just holds all that nice common code to handle all these kind of cool services and things. This communication on the same machine is a local network. It's not at this point a distributed system, so you don't have to worry about those sorts of concerns. It's just as long as those two processes are running, they can communicate. And then that would then route any traffic from node to node through those JVM proxies. So now, by having these generic proxies, we can share all of that code we like for all of those common concerns. We don't have to worry about version drift, and we can reuse code across very different technology stacks. Effectively, in this example here, my Node.js service down here is effectively making use of Java code running on a different runtime, which is quite a nice idea. So this works actually really well. And so the Linkerd took that model and put it on steroids. And they said, well, what we'll do is all service communication will now go via these proxies. And so to configure and manage those proxies, we'll have sort of a control plane, where you can set out how you do these, how many retries should we do? Do we need to push out some new certificates for signing our JWT tokens and those sorts of things? That can be done from a central location. And that's really what service meshes are now doing. There are some different models around service meshes. You've kind of got the local proxy model and the Sidecar model. The Sidecar model works well with Kubernetes. The Sidecar model, for each service instance, you have a matching proxy instance, and you deploy those two things together. So things built on Envoy tend to do this. That's where you deploy a pod with those two pieces together. And so each service instance has its own copy of the proxy. And that means it's easier to configure that proxy specifically for what you need for that service instance. These sorts of models where you have all the service instances on the same machine using one proxy, that tends to happen with the JVM-based proxies that are heavier in weight. So Linkerd version 1 does that. Linkerd version 2 used to be called Conduit, now works this way. That's how Istio works. So there's a whole bunch of common concerns these things can handle: load balancing, traffic routing, service discovery, tracing, and a lot of the security stuff we've talked about today. Istio's got all kinds of stuff they're working on to make things like MutualTLS almost an out-of-the-box experience. It's not quite there yet. I think Linkerd so Istio's taken a while to get to a good 1.0. So I think these ideas are really powerful for microservice architectures, especially if you're deploying onto container-based platforms that work with these service meshes, because things are done for you. Of course, on the cloud platform, you've already got services that do a lot of this stuff for you as well. A lot of those API gateways that you get will help solve some of these issues. Not all of them, but some of them. We've covered a whole bunch of stuff today. We've talked about patching and passwords, which seem boring, but actually get a bit more complicated in a microservice environment. We talked about secret stores. If you like secret stores, you won't regret giving Vault a look. We've also talked about some different concerns around transport security. I didn't want to talk about all the different types of transport out there. I wanted to say, when you look at the transport you're using, what are the things you need to worry about? We looked a bit about authorization and authentication models, both for service-to-service and also for human being type interactions, and how we infer, well, not how we understand who a person is in a call that might be happening, say, 5 or 10 network hops downstream, and touch very briefly on service meshes. I've got loads more information on security over on my website. You can get these videos on the Safari platform, and you can find information here. And I've also got a new video all about serverless, really fast as well on my website. We are virtually on time, but I'm more than happy to hang around and ask any questions that anyone has. I hope you've had a nice time. On the way out, please do vote. If you've got any feedback for me that you want to give me that's more than just a color, feel free to just hurl abuse at me on Twitter or something like that, or drop me a note. But thank you very much indeed for your time.